Okay, AP Statistics students, this should be the last video that I am making for you before the AP test next week. So, this includes two sections, 10.2, Comparing Two Means, and 11.2, Tests about a Difference in means. In both cases, we're looking at the difference in two means. In one case, we're doing a confidence interval, comparing. In the other case, we're doing a hypothesis test. So, just a little bit of background again about the sampling distribution of the difference between sample means. So suppose we have two populations. We choose samples from each population. The samples do not have to be the same size, so the sizes are N1 and N2. And each sample has a mean related to some parameter that we are interested in. So we have the mean 1 and mean 2, mu1 and mu2. And we also have standard deviations, sigma 1 and sigma 2. So shape. When the population distributions are normal, the sampling distribution of the difference of the sample means, x1 bar minus x2 bar, will be approximately normal. In other cases, excuse me, when we don't know about the populations, the sampling distribution will be approximately normal if the sample sizes are large enough. And in that case, we say N1 and N2 both have to be greater than or equal to 30. Otherwise, we would need to make graphs and look at the graphs to see if they meet the criteria, and there we would be looking again for no significant outliers or skewness. Center, the mean of the sampling distribution will be the difference of the means, okay? And spread, the standard deviation of the sampling distribution, is this formula, and we'll talk more about that later, as long as each sample is no more than 10% of its population. So we still have the 10% condition. All right, so comparing two means is a lot like comparing two proportions. So we still have the same formula here at the top. We take the variances, add them, and then take the square root. But in this case, instead of having our P1 minus P over N, we have this formula here. This is the formula for the standard deviation. So we have sigma 1 over square root of N1, square root of N1, and then we square that. And sigma 2 over the square root of N2, we square that. So when we simplify, we end up with this formula right here. Of course, we don't know the standard deviation, so we will substitute the sample values, S1 and S2, and call it the standard error. So we've seen this before, but the formula is a little bit different here. So for a confidence interval, this is the formula for a confidence interval. We take the difference of the means, plus or minus. We're still using T, so T star, based on the level of confidence you're looking for in the sample size, times the standard error. And for a significance test, the T value is equal to the difference of the means, sample means, minus the difference of the population means. In this case, we won't know them, but we will have hypothesized values, divided by the standard error. So here's an example, and you can pause this video and read through this. But basically, we're interested in whether or not people will eat more if they know that they're being given refills versus if they don't. So you might want to pause this video for just a minute and just read through this example. I'm not going to read it to you. But here's our sample data. In an ordinary bowl, we have 27 individuals who are eating out of an ordinary bowl. The mean amount of soup that they ate was 8.5 ounces with a standard deviation of 6.1. When the bowl was refilling by itself, they were not aware of the refilling. They ate a lot more, as you can see on average, and the standard deviation also is wider. So, if we were going to do either a hypothesis test or a confidence interval, we have to check our assumptions and conditions. Okay, so can the researchers use their data to make inferences about the role of visual cues in determining how much people eat? So first of all, now this comes from a different textbook, so it looks a little bit different. Independent groups assumption, we need to randomize the treatments, which we did. So the subjects were randomly assigned to their treatments. The independence assumption, the amount consumed by one person should be independent of the amount consumed by others. And then the nearly normal condition. So because 27 is less than 30, we have to look at our histograms. So here are some histograms we will look at. Notice there is skewness, but it's not that strong, and they're might be an outlier, but not really, not an obvious outlier for both groups. Okay, so you have to look at the graphs and say, okay, close enough. So let's see. First, we're going to look at the confidence interval. So state, estimate. In a confidence interval, we're always estimating. Estimate the difference in the amount eaten with a refilling bowl versus a regular bowl at 95%. So plan. If the conditions are met, use a 2-sample t interval. That is the name of the test, 2-sample t interval. On the calculator, it is 2 prop t. Oh, no, I'm sorry. What is it on the calculator? I'll come back to that. All right, 2-sample t interval for a difference in means. Here's our data again, just so we can see. Conditions we checked on the previous slide. So for the do step, here is our formula. Okay, actually, I think I have the calculator down below. So here's the formula. So the difference in the sample means plus or minus 2.056. Recall where that comes from. We're doing inverse t. And inverse t for a 95% confidence interval, the area would be 1 minus 0.05 divided by 2, which would be 0.025. And then we multiply that by n minus 1. So in this case, which n do we use? We use the smaller of the two n's minus 1. So 27 minus 1 would be 26. Okay, so that gives us this answer right here. So the interval is from 2.088 to 10.312. On the calculator, here's the name of the formula, 2-sample t interval. And we would use statistics here because we have the statistics to use. So these are statistics, whoops, versus later on you'll see an example, and maybe we have seen an example where you use data and you enter the data into the lists in the calculator. Okay, on the calculator you get a slightly different answer, and that is because of the way that the t-star is calculated. There is a more complicated formula that the calculator uses, but we're not going to use it here. All right, so the conclusion, I'm going to run out of space here. Let me see if I can just kind of move this stuff out of the way and move my conclusion up so you can see it. Okay, move this up. Okay, so here's my conclusion. I'm 95% confident that the interval from 2.088 to 10.312 captures the true difference in amount eaten in a refilling bowl versus an ordinary bowl. And this would be by people who are similar to our subjects in our test. Note that since 0 is not a plausible value, we can conclude that there is in fact a difference. Okay, now this one is the hypothesis test. So let's look at the hypothesis test. Significance test, another name for hypothesis test. Did one group eat more soup than the other? So this is just a yes or no answer. Null hypothesis, there was no difference. Mu1 minus mu2 equals 0, where mu1 is the amount of soup eaten from a refilling bowl, and mu2 is the mean amount of soup eaten from a regular bowl. Alternative is that it's not 0. Notice we're not saying that one group is eating more than the other. We're just saying they're different. There's a difference. If the conditions are met, we use a 2-sample t-test for a difference in means. We did the conditions previously, so we're not going to do them here. So the do, here's the formula. Plug in the numbers, and you get your t value. And then to calculate the probability, we do t CDF, okay? Lower 3.1, which is right here, upper 1,000, because we want to know the probability that it's, actually this should be a two-sided test. So we're going to use this t value, lower, upper, degrees of freedom 27 minus 1 gives us this, and then we have to double it. So we have to multiply this times 2 to get our probability of 0.0046. Okay, so now again, I'm out of space. So what I'm going to do is take this here, copy it, put a new slide, paste it, and we'll look at this. Okay, so this should be 0.0046 because we had to double it. But still, because this is less than alpha equals 0.05, we reject the null hypothesis in favor of the alternative. We do have evidence to say that there is a difference in the mean amount of soup eaten from a refilling bowl than from an ordinary bowl. Okay, so there you have it. That is confidence intervals and hypothesis testing for a difference in means.